Let's talk about first order differential equation. So the general form of first order differential equation can be written as dy dx equals f of x comma y. Now, can it be solved? Well, sometimes if it has some congenial form, then yes, of course it would be solvable, but in general this is not always solvable. Okay, sometimes it's also written with the minus sign, and sometimes it's also written as a rational function, which is a ratio of two functions. So sometimes you'll also see this form, negative p of xy divided by q of xy. Again, this is the general form. This doesn't mean this equation is solvable. Our goal is to see some of the forms which gives us an idea about how to readily solve that equation given the congenial or allowed form. If that is the case, then yes, we can solve it. We can always solve it in theory by numerically integrating, but that's not an analytical solution. What we'd like to find is an analytic solution which allows us to have exact expressions of the solution. So the first type we would like to explore, so type is called the separable form. The separable form. An equation is separable if it has this particular form, dy dx equals negative p of x over some function q of the variable y. Now, this can also be written equivalently as p of x dx plus q of y dy. I think why this equation is called separable can be understood readily from the form written on the right hand side. So as we can see, the function of the variable x and the differential of x can be written entirely on one side or in one term, while the function of y and the differential of dy can be written entirely in the other term, and that's how it literally displays the characteristic of separability. When we can do that, then it is apparent that we can immediately integrate this equation from points x0, y0, where both x0 and y0 are constants, to x, y, where x and y are variables. Remember, after solving this, we want to find the solution as an equation, which is also called the integral curve. So therefore, the solution can be written as integration from x0 to x p of x dx plus integration from y0 to y q of y dy. And that is equal to 0. Okay, so this should give us our solution. Let us now explore an explicit example where this is the case. The differential equation that we desire to solve is indeed a separable form. The example we choose here is that of a falling object through a viscous medium which has quadratic drag. So an object which falls under such a force is characterized by the Newton's second law of motion, where the external force is a drag force with dependence as the square of velocity. So the dependence on the velocity is displayed as a square of velocity. So in that case, we have F equals ma, and this external force is comprised of two components. One is the object falling due to the influence of gravity, and another is the drag force, which is dragging this object in the opposite direction, opposite to its velocity, so that would be F drag. And before these two forces balance each other, the object continues to accelerate in the downward direction with an acceleration A, and which we write here. So altogether we have m, then we have dv dt, which is the acceleration, and this is equal to mg minus F drag. And this drag force, as we have just spoken, is proportional to the square of velocity. So we write the proportionality constant as b. So finally we find out the form, which is m dv dt equals mg minus bv squared. As it is evident from this equation, we see that v is the only dependent variable and t is the only independent variable. So this is an equation of first order, and notice that this equation is not linear, but it is separable. How is it separable? Let us have a closer look. But before we do that, let us clarify ourselves on the note of a bit of technicality. The first technicality that we'll have to clarify is that of the initial condition. So we assume that v, the velocity, at t equal to 0 is written as v naught, which we take to be 0. Remember, this is not a general condition, this is the specific initial condition that we have chosen. All it means is that at the beginning, when we have started our stopwatch, the object was at rest and it was released from rest without any initial velocity. So initial velocity is 0. We also specify that since the drag force grows quickly because its dependence on the velocity squared, that means soon enough the drag force will be equal to mg, the gravitational influence, and one will balance the other. And this will definitely be the case when we allow t to flow off to infinity. That means after a long time the object will fall at a constant velocity. So we define the velocity as t tends to infinity as v infinity, and we know this is a finite value, at least according to our intuition we can surmise that, and that can be defined as the value when the drag force catches up with the gravitational influence. So in that case we'll have 0 on the left hand side, where we have m times a, because the acceleration is no longer acting, remember, because the forces balance on themselves, so the acceleration is 0, therefore the left hand side, which says ma, will also be 0. On the right hand side we have mg minus bv squared, and this v is actually the velocity when time goes to infinity. We shall call this velocity as the terminal velocity. So this allows us to write the terminal velocity as the square root of mg divided by b. So this v infinity is equal to square root mg divided by b. So Since that is the case, what we can do is to use this expression to replace the mg. So what do we get? We get mg is equal to b times v infinity squared minus b times v squared. So therefore we end up with m dv dt equals b times v infinity squared minus v squared. We can immediately separate the two variables as follows. So we can write dv over v infinity squared minus v squared, and on the right hand side we have b divided by m into dt. We can also simplify the left hand side, where we have this function 1 over v infinity squared minus v squared, by using the method of partial fraction. So we can take this function and say that 1 over v infinity squared minus v squared can be written as some coefficient divided by v infinity minus v plus b divided by v infinity plus v. And then if we multiply everyone by v infinity squared minus v squared, what are we left with? We're left with 1 on the left hand side, and then a times v infinity plus v on the first term on the right hand side, and b times v infinity minus v on the second term on the right hand side. Since the last statement we have arrived at should be treated as an identity for the variable v, that means it's true regardless of the value of v, what we should do is to choose special values for v which will yield the values of a and b. And the first step for that is to say v equals v infinity. Choose that value, and what does this statement entail in? Well, 1 equals a times v infinity plus v infinity, so that's 2 v infinity. But the next term is v equal to infinity, when substituted yields 0. So therefore the whole term is 0, and it ends up with a equals 1 over 2 v infinity. What about choosing v equal to negative v infinity? Does that help us in any way? Yes, of course. In this case, the first term, this one, becomes 0. And what about the second term? Well, the second term yields b times this one yields 2v infinity as before, and so b is also equal to 1 over 2v infinity. So what do we have? We have 1 over 2v infinity times, well, I could say minus 1 over v minus v infinity. See, I have taken out a minus sign from here, and then the second term is 1 over v plus v infinity, and that is equal to b divided by m dt. Well, I've forgotten a dv here. If we'd like to integrate over the result now, what do? Well, this is the simplification, and we integrate the variable v from 0 to v, and then here 0 to v as well. Well, technically, these two variables cannot be the same because the integration variable has to be the dummy variable, so I'll put a prime over these things. And same goes for t as well, so I have to integrate from 0 to t. Of course, I'm leaving the constants out of the integration wherever it is possible. And so what do I find? Well, if I factor out 1 over v infinity, the first integration gives me log of v plus v infinity, and then minus, if I plug in 0 in the place of v prime, then I get log of v infinity. Similarly, minus log of v minus v infinity, and then we have minus, well, plus in this case, and then log of minus v infinity. Well, don't worry about the minus sign because v infinity is not the one to be responsible for this. Remember, we forcefully pulled out a minus sign, so that's why this minus sign is here for. So on the right hand side we have v divided by m times t. If we rearrange this or try to simplify this, so 1 over 2v infinity, but inside we have, what do we have? We have v plus v infinity divided by v infinity, and then minus, what do we have? We have log of v infinity. Well, that's what we are doing. We're putting v infinity first and then minus v, so that we have a minus sign here, but that minus sign is compensated by this minus sign, so we have v infinity, and that is equal to b over mt. So that minus sign wasn't actually a concern. So then, since we have this common denominator here and here, if we take these two logarithms and put them together, then according to the law of logarithm, what happens is this v infinity cancel the other v infinity, and we're left with v infinity plus v divided by v infinity minus v. And that is equal to b divided by m times t. Well, can we simplify this further? Yes, we can. So we have to write e to the power 2v infinity times b divided by m times t is equal to, well, what is it equal to? It's equal to v infinity plus v divided by v infinity minus v. Can we simplify it further? Yes, because the solution has to be written for v, so v as a function of t. So how can we solve this? Well, we can solve it by basic algebra. Well, first of all, v infinity is equal to square root of mg divided by b. And if we multiply that b over m, so here we have b over m, and then of course t, what do we end up with? We have this b cancels the square root of b, and this m cancels the square root of m, and so we end up with gb divided by m. So it's a matter of common calculation that we have v divided by v infinity equals e to the power 2. Well, how can I write this quantity? Let me call it something else. Let me call it 1 over capital T, which will have the dimension of time if you calculate it correctly. So I encourage you to check it out. So then we end up with 2t over capital T minus 1 divided by 2 e to the power 2t divided by capital T plus 1. Well, we can simplify it further by writing this to be e to the power t divided by capital T minus e to the power minus t divided by capital T over the same thing in the denominator, except for a plus sign instead of a minus sign in the middle, and this is our result. So quickly we divide both things by 2, and notice on the numerator we have the sine hyperbolic function, and on the denominator we have the cosine hyperbolic function. So our solution gets even more simplified, and we end up with v equals v infinity, and then sine hyperbolic t over capital T, and then cosine hyperbolic T over capital T. Well, finally, v equals v infinity, and then we have tan hyperbolic T over capital T. So if we substitute all the constants in terms of the original parameters, what do we find? We find v equals square root mg divided by b, and then tan hyperbolic, and then we have square root of gb divided by m times t. And this, ladies and gentlemen, is our result. Let me box it up here. So this actually expresses v as a function of t, which is also subjected to the initial condition that we have emphasized at the beginning.